All right, so thank you again for staying this late. In this part, my name is Pramey Upadhyaya. I'm from Purdue University, and I work mostly on aspects of spin and magnetism, and for their potentially quantum properties or classical properties for information processing applications. And this is in this talk, in this part of the school, what we are trying to do is shift a little bit gears towards. So you have heard in the morning sessions that these quantum materials have exotic properties. They can have things like fractionalized excitations, hydrodynamic flow, and things like that. And now the idea of present talk would be how can we potentially exploit these properties to create some information processing devices or applications which, for example, current present-day electronic devices we cannot engineer that in current devices. Right? So that's this general theme along which we wanted to focus on in the second part of things, and I'll kickstart that with one application, which is that of quantum computing. The fact that we can exploit these quantum coherences that are present in these devices to do computing in different ways. So that's the sort of main topic of my discussion today. There are basically, to put things in context, this is what I wanted to highlight here. And I'll also be doing this very informally, in the sense there will be notes, I'll be doing writing, although my writing is much worse than Srijit's, so I hope it's still readable, and if there are any questions, feel free to ask me if there's something is not clear on the report. Okay? So to put things again in perspective here, as I mentioned, we're focusing on these sort of applications of quantum materials, and there are, broadly speaking, three main categories that you may have already heard about, where there's the computing applications. There you can use these for doing sensing in a different way than what you could have done in the classical world, and finally for doing communication. Okay. And within the computing part, there are various ways that people have really thought of making computation models for exploiting quantum principles. There are the famous gate-based models. There are models based on something called adiabatic quantum evolution. And then more recently, people are starting to focus on more special purpose things like machine learning, exploiting quantum mechanics. Right? And that has also given sort of birth to more like classical but still quantum-inspired ways of doing information processing. One very famous example that is recently emerging is those so-called probabilistic computing. Okay? So in this school, what you'll see is various people talking about different aspects of things. For example, I'll be focusing this talk on the gate model of quantum computing, and this can be actually realized in various different platforms, different kind of quantum materials. My focus would be on superconducting platform. I think you'll hear from Mahesh on spin-based systems. Then there's another professor from Purdue University who will talk about these exploiting topological properties like the ones that you heard today in the morning, using Majorana-based systems for creating these platforms. There are others, of course, which we'll not be able to touch in the school. Particularly the communication aspects, we'll not be talking too much about that. But you will also hear things like machine learning aspects of it from another postdoc who is there in Purdue, works in Professor Sabre Kai's group, who does a lot of quantum machine learning. And finally, Professor Supriya Datta will talk about these probabilistic aspects of using quantum-inspired probabilistic computing. So that's just to put things in a bit of nutshell and give you where we are going towards with this applications perspective. And as I mentioned, this talk's focus is, I want to convey two main messages in this next 2 hours. If I go back on this drawing now, here's a sort of cartoon representation of what a universal gate-based quantum computing model is. So this is one message that I want to deliver. How should we think about that? And the second message that I want to deliver is how one can build such a machine using superconducting materials. So those are the two parts, and these are a few examples. For example, this is taken from IBM, who is building these machines, and you can access them in cloud present day. Okay? So very elementary introduction to these two aspects is my goal in these lectures. Okay, and feel free to interrupt me and if you have any questions in between. Okay. All right. And in order to get that goal, here's the three main points that I will be conveying about. First of all, what is this gate-based quantum computer? Why even build them? And how to build them using superconductors. The prerequisites that I have assumed for this particular talk is kind of like senior level undergraduate level quantum mechanics. Things like postulates of quantum mechanics, perturbation theory, what is harmonic oscillator, and what are two-level systems. So these kind of things I assume that you have knowledge about. And I should at this point take this opportunity to sort of apologize in case this has not been your background, and also the experts. That I will not be going into talking about like expert part of these quantum models. But again, feel free to stop me and reach out to me. I'll be happy to guide you to the references that have been used. Okay. I also assume a bit of circuit knowledge, things like capacitors, inductors, and things that we study. Okay. Okay. All right. So with that, let me start what is this field of quantum information? And to me, as a student, these two quotes kind of very nicely summarize what the field is of quantum information, given by some of the founding fathers of the field itself. So in the first quote, and let me just read the quote by David Deutsch, he's mentioned that computers are physical objects and computations are physical processes. What computers can or cannot compute is determined by the laws of physics alone and not by pure mathematics. What he's trying to convey here is, again, the fact that you can think of an abstract model of computation, but in the end, you will have to realize it on some hardware platform, on some physical platform, which is governed by laws of physics. So you better make up rules which are also compatible with those laws of physics. Only then those models will see the day of the light. Right? So that's what he was trying to convey here. And then one can naturally ask, what are these laws of the world? Which governs things, and that's sort of nicely summarized by Richard Feynman, who says that nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. It's the fact that these laws are quantum mechanical in nature. Okay? Although all the present-day technology that we use today is based on classical mechanics. Right? In sense that, okay, quantum mechanics does play an important role. The fact that semiconductors exist, quantum mechanics plays a very important role, that there's band structure, electrons are like waves. But after that, we sort of forget about quantum mechanics. We say that these are like effective particles, classical particles, and then we can work with them with effective classical behavior and model everything based on that. Right? But there are some very nice and intriguing aspects of quantum mechanics, things like they can be in superposition, you can entangle two particles together, and the kind of things that you heard today, that they can have these sort of fractionite excitations, you can behave correlated in a fashion, do hydrodynamic flow, and things like that. Such aspects we currently neglect in all our present technology. And the fact that we can actually exploit them to create new technologies is a very interesting field that only recently people are starting to focus a lot on. Okay. So quantum information is trying to exploit laws of quantum mechanics to do models of to build models of computation, although present models are all classical in nature. Okay. So what can we do extra if I give you some new rules of the game? What can we do new? Okay. So that is the main driving force for the field. Okay. And in order to highlight this further, let me sort of build three main important questions if we want to build a model of computation, what we think about as the three main questions that we have to first figure out as answers. First question is, whatever you're trying to process, how are you encoding the information? How do you store this particular piece of information? Then you have to tell me a rule for how that information can be manipulated. And once you have done the manipulations, which is information processing, then you have to read the result. So how are you allowed to read the result of those three things? Okay? So these are the three main questions you want to answer if you want to build any information processing technology, right? And answers to these three main questions are governed by the laws of physics, right? So you cannot give arbitrary answers to this. And just to highlight that fact, let's sort of give you a very bird's eye view of present day digital classical computation. How does it answer these three questions? Okay, so, and this may be, most of it might be just a reminder. So for example, how is information encoded in present day technology? The basic building blocks are what we called in this special model of digital gate-based computing, classical computing, the basic building blocks are so-called bits of information. Okay? These are nothing but just, you can view them as classical two-level systems, which can take two values. Right? For example, it could be like a magnet pointing up or pointing down, and those are your zeros and ones. So you break down all the information in this little basic building chunks called bits of zeros and ones, and then what you do is you just essentially combine these essential building blocks to create a more complex information. For example, you can have an n bit encoded, where I can tell you the state of this bit by just specifying what is the state of each of these magnets, and that's like a bit string of some n numbers. Those are your n bit string which has the information. Every information is just written down as this, and then you manipulate this piece of information to do processing and finally read the results out. Okay. So that's essentially main message that I want to give from this slide is the fact that all information right now can be broken down into classical two-level system, which can take two values. Each of the bits can take two values, either 0 or 1. Right? So that's how you start, by encoding information. Then once you have this information encoded, the next question you ask is, how do you manipulate this information? So think of, let's say, there's a space of all values these n bits can take. Those are all the space. And manipulation is nothing but translating one of this Boolean number into some other Boolean number. So each bit, you can either change the 0 to 1, 1 to 0, or keep it the same. Okay? So this is how you manipulate and move from one encoded information to another encoded information, keep on doing various kind of manipulations. The objects that do this manipulation, we call them gates. Okay? So you may have heard of things like AND gates, NAND gates, OR gates. It takes basically bits of information, convert them into some other bits. And that allows you to move in this space of bits and create, that's essentially what we call this processing of information, to change this information. Those are the laws by which you will change the information. Okay, and finally, how can these results of these manipulations be read? This is almost like a non-question for classical systems. Whatever is the information, you'll just read that. For example, if 0 is there, you'll read that to be a 0. If there's 1, you just read that to be a 1. Okay? Barring any sort of errors that can occur, for example, just your reading measurement instrument can have errors. However, you can always correct for them, and that's the so-called whole thing of error correction. And combining all these principles together, you build a model of computation. Right? So that's a very quick sort of review of what classical systems look like. Maybe I pause here for a minute and see if there are any questions on this. Okay, good. All right, so here's a cartoon way of seeing how a classical digital information processor would look like. It will consist of essentially these n bits. So you'll input some initial state, initialize this n bits into some initial state, and then you keep on applying this sequence of gates to manipulate this information and finally read them out to generate an n-bit output number. Any machine that does this is a gate model of computation. Now, there is a sense of creating a universal machine which can compute anything, right? And the idea is, if you given some initial state, if you can convert that initial state into any other n-bit number, any other arbitrary n-bit number, then this machine will be called a universal machine. Right? So you can, if you can design gates in between which can take this number into all full space, cover the whole space of these, any general Boolean function you can implement, then it is a universal machine. All right? And for practical purposes, it's good if we can do this with some subset of universal gates. What I mean by that is, anytime you want to implement a new function, you should not come up and try to build a new function from scratch. Okay? There are some basic gate sets which you can just combine and create this whole universal machine. So that if you can do, then you have a universal computer, and that's what we present day all our machines are. Right? So they are trying to do this. So to just give you an example, the so-called NAND gate is in itself, or not a combination of NOT and AND gate, is a universal gate set machine, because you can construct any Boolean function just by concatenating these things together. All right? So that's a quick overview of what a universal digital classical computer is. Now, what a universal digital or gate-based quantum computer is, it tries to mimic this design in the quantum world. Okay? But the rules of the games will change now, because now the laws will become quantum mechanical. Now, but this design or this architecture, if you want to capture in the quantum world, that particular machine will be called a universal gate-based quantum machine. Okay? And that's what we'll focus on in the next part. All right. Just cartoon-wise, I want to represent. So any function you can just break down into some universal gate sets. Okay? So these type of pictures we'll also draw in the quantum domain. Okay. Okay. So let's start take each of these questions and try to answer what new thing quantum mechanics brings in to the game. Okay. So the first thing that we want to focus is how information can be encoded. Okay. And just for contrast, here we have talked about the basic building blocks are these bits, which can take either value 0 or 1 in each of these bits. On the other hand, if we make these magnets quantum mechanical, okay, or like focus on individual constituents like electron spins, they start behaving quantum mechanically. Okay. And the states encoded in the spins can be represented not by just two numbers, 0 or 1. It actually covers a sphere, the full space of sphere, which is famously called the Bloch sphere. And in order to see that, this follows from the basic first postulate of quantum mechanics, where let's see if we can try to quickly derive this aspect that it becomes, the information becomes, rather than just 2 points, 0 or 1, it becomes a full sphere. Yeah. So
traditionally, what we use in CPU architecture is like MOSFET, FinFET, and others just to kind of do that, transistor.
yes.
Like etching and all of that. So how do we etch qubits on the silicon?
Oh, so physically how we realize this hardware part, we'll talk about that in the superconductor part, superconducting aspect. But you can do similar fabrication process. You can design these qubits. You can design them in semiconductor systems themselves. So you can have doped semiconductor systems which can host electron spins which behave quantum mechanically, or you can design circuits in lab which follow similar type of fabrication process. You can design like LC circuits, and that's what we'll talk about in superconducting materials, and cool them down. They'll start behaving like quantum bits, and we'll see how.
Have the problem like we have to keep it isolated so that it doesn't.
Yeah, that's the main issue, right? That's why we have to cool them down, dig holes, and build them in this sort of big dilution fridges and things like that. That's the main reason for preventing. So to make the quantum evolution, for such the rules that we are talking about, for them to be applicable, we need to do all that. Okay, and that's the main challenge. How do you scale such a system, make systems which are much more robust, and perhaps things like topological protection could be exploited for doing things at that level, or there are schemes of error correction that one has to be able to demonstrate.
That's the most expensive thing, like computational noise, filtering the error and all.
Yes, that is absolutely right. So, and that is why we don't see quantum computers today at that scale. Everyone doesn't have a quantum computer. And that's probably not the vision too. The vision would be that such machines will be really special purpose machines which are dedicated to tasks which classical computers cannot do. Okay? And think of them like supercomputers sitting somewhere, which you would be exploiting for doing some special task. It will not replace our mobile phones, for example, right? Yeah. All right, good. Any other questions? All right, so the first thing that I want to highlight is there's a stark contrast here. Okay, so in classical system, the states which I encode in a single bit are just 2 values, 0 or 1. In a quantum mechanical system, that becomes a full sphere of information. Okay? It's a continuum of information that can encode in just a single quantum bit. Right? And the reason for that follows from essentially the first postulate of quantum mechanics that we hear. Right? So what are the laws of quantum mechanics? Well, it says the first postulate says that any state of a quantum system should be represented as a vector in Hilbert space. Okay? This is something that you have heard in your quantum classes. So what that really means, this word, is, let's say if I have a 2-state system, so it's still a 2-level system. If I want to describe this in quantum mechanically, it should be represented by a vector like that, a column vector, where each of these things is a complex number. Okay? And the square sum, if this is a closed quantum system, the square sum of this should be 1. Okay, so it's a unit vector in a complex, in a Hilbert space. That is what every system has to be in quantum mechanics. That's what it says. But how many complex numbers satisfies this constraint? There are continuous, very large number of complex numbers that can satisfy this thing, this constraint. Right? And that's why even in a single 2-level quantum system, I can encode a large number of complex numbers in the same system. In fact, you can see here the formula that's written here is cosine theta by 2 e power I phi sine theta by 2. This satisfies this constraint. Okay, so this is, if you square this, they will add up to 1. Okay, those are 2 complex numbers which satisfy my first postulate of quantum mechanics. And as a result, my state is now parameterized by 2 parameters, theta and phi. And these are continuous values which can take, this number can take. And those theta and phi can be represented compactly on a sphere. And that's why the information that is encoded in this, by first postulate of quantum mechanics, can take all these possible values. Okay, so even a single bit, not just north pole and south pole, those 2 values of 0 and 1, it can point in any other direction as well. Okay? And that is what we know by the goes by the principle of superposition. So the states are now given by superposition of this, and these coefficients just tell how much you mix the 2 states together to form this particular final state. So then in this jargon, people also talk about this as it can be 0 and 1 both at the same time. Okay? It can take all these, so cat can be dead or alive. So this fact that this is a superposition, a single bit can have information encoded in all this. So this is immediately a jump in the amount of information you can encode in just in a single bit that quantum mechanics allows you, which was not there in the classical digital machine. All right? So that's the first main point I want to highlight as the answer to the first question, that how you encode information in the system. Okay, Okay, and we'll exploit this particular fact. The second thing is, and this is something even more strange, where if you start to combine different blocks. So how can I make a more complex block? As we discussed, I can start combining these basic building blocks to form a bigger and bigger, store more and more information. Okay, and how does this space change as I start combining these blocks? Well, what quantum mechanics tells us, the space starts growing exponentially. Okay? So for example, if this was n bits, how many information I need to give you to specify a singular state of this thing? I need to tell you n numbers. All right? I just need to specify what is this. Is it 0 or 1? Is it 0 or 1? And all those numbers, if I specify these n bits, I completely specify a particular combined state of the system. All right? What happens if I start combining these quantum mechanical bits together, these qubits together? Well, the postulate says that actually the Hilbert space adds up in an exponential fashion. Okay? What specifically that means is, in order to specify a state, I need to construct a new basis for this combined system. For an original system, there was a basis of this 0 and 1, and whose superpositions was specifying the state of one particular bit. Now the basis state itself grows exponentially with the number of bits. So for example, if I want to just specify for 2 of these bits, the basis states will become, for just 2 of them, are given by 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 numbers. I need to now specify 4 complex numbers corresponding to each one of them to completely specify the state of this combined 2 bits together, 2 quantum bits together. Okay. If this was 3, then I get 8 possibilities. So it goes 2 power n. Okay. If I have n bits of information, I need to specify 2 power n complex numbers. That is an exponential growth in the amount of information, as opposed to n bits here, which for specifying a particular state, I need to only specify you n numbers. Now I need to specify 2 power n complex numbers to you in order to specify this. Okay? So that is again a fundamental postulate of quantum mechanics. That's how systems combine in quantum mechanics. That immediately again tells you that there's a lot of information that can be encoded in these quantum systems. Okay? To give some perspective, you have 15 or 100 qubits, well-constructed closed quantum qubits. If you can create, that's 2 power 50 or 2 power 100, a very large number of information that those bits will have. Okay? Much larger than the total number of atoms, for example, that we know in this world. Right? So that's one of the pull of creating information in these quantum systems. Right? So that's about encoding information. But again, nothing comes for free. We'll see there's how do you read information out of these systems. We'll come to that particular point. And that is what will make things really challenging, actually. It's not that you just build a quantum computer and you'll get everything for free. Okay, so, and we'll try to highlight this particular point once we come there. Okay, so then once we have this information, the question comes is how can you manipulate this information? Sorry for the very busy slide. Let me try to go slowly by it. So as we discussed in classical systems, the thing that we are doing was we have an n-bit number. We are just transforming it into some other n-bit number. In quantum mechanics, we have this n-bit vector, right, with complex numbers, and those are translated into some other complex number. Now, for this other state to be still a well-defined state of a quantum system, should also have this unit length. It should also add up to vector 1 for it to be specified as a state of a closed quantum system. So the transformations that are given by matrices now. So you have a vector, it's transformed into another vector. The transformation is given by matrices, and not just any matrix will do. For closed quantum system, those matrix has to be a unitary matrix. Okay? Because we have to preserve the length of the vector, the matrices that do that by definition are unitary matrices. All right? So in quantum mechanics, any input state can be manipulated into output state, and the manipulation is given by a unitary transformation. That's the postulate of quantum mechanics, right? And for example, if you want to talk more in the physics language, this unitary matrix is constructed out of Hamiltonian, and this evolution is given by the Schrodinger equation, which preserves the length of your quantum states. Okay? So Schrodinger equation or unitary evolution is how you can manipulate. So that's the rule of the game. You cannot put any arbitrary matrix, but it has to be a unitary matrix. Okay? But again, important to contrast this with the classical system. So if I go back here, what you can do classically, if you're given a 0, you can either make it 1 or keep it 0. Those are the two things that's possible. Here, if I give you a state, there's sort of infinite number of transformations I can do. I can rotate it by some arbitrary number, arbitrary degree, angle. Okay? Each one of them that preserves the length of this thing is a valid unitary transformation that's allowed in the quantum mechanical world. Okay? So the number of gates that I can implement, quote unquote gates, these unitary matrices, are almost like infinite. in this quantum mechanical world. Okay. All right. So that's the rule of manipulation, which is again should be contrasted with classical. And when we'll think of this being universal, well, it's the same idea. We'll call this a universal quantum computer if, for example, here's the space of all your n qubits states that n qubits can take, and if given any initial state, if you can do arbitrary transformations of this initial state to cover this whole map, okay? If you can transform any initial state to any final state, if a machine can do that, if you can construct a machine like that, that will be called a universal quantum computer. Okay? And again, for practical purposes, we don't want every single time you want to do a transformation, construct a new machine. And there should be some basic gate set that you can combine to create this arbitrary unitary transformation. Fortunately, there's a theorem which proved that it is possible to go in some precision absolutely close to this transformation by just constructing any unitary transformation, to break them down into universal gate sets. Okay? And that one example of such universal gate set is given by if you combine single qubit rotations, which was rotations on this block sphere of single qubits, with a so-called C0 gate, or it's a 2-qubit gate. That is, it takes in input 2 qubit lines and create an entangling type of operation. If you can, and I'll talk about this gate a little bit more, but if you combine these two gates together, then you can realize any universal quantum computation. Okay? This is just an example. There are many such universal gate sets, just like in classical system. There are many possible universal gate sets of operation. Okay? So then, based on this, the concept of a universal quantum computer is nothing but a machine which can take n bits of information and translate n qubit states and translate into any arbitrary qubit state by some finite gate, by just combining some basic gate structure. Okay? This is what, if we build in lab, will be called a universal gate-based quantum computer. All right? Okay. And just to give you an example of what this C0 gate looks like, what it does is it acts, actually this is the symbol of that gate. It acts on 2 qubits. So 2 qubits comes in, and the state of those 2 qubits will be translated into some other state over here. And the basic idea is, in order to give its full functionality, what it does to any generic state, all I need to tell you is what it does to the basis states of these 2 qubits, because then I can make any arbitrary state just by combining these basis states and see what the transformation will be. So what it does to these just basis states, if I can specify that, I will completely specify what this gate would be. Okay? And the basic specification is the following. There is a line which we call a control line and one line which we call a target line. That is to say, each of these lines represent a qubit. Okay? So given any particular input state of these 2 qubits, the operation of this gate will be to transform this particular state into some other state. For that, I need to specify which one I'm calling a control bit and which one I'm calling a target bit. And the operation of C0 is, depending on the state of control, do something to the target. And what is that something that we do? Which is the NOT operation on the target. Okay? So then it's called a control NOT gate. So for example, if I want to fill this table up, what I will do is, given this, if this was the input state, what will be the output state of this operation? Well, if control is 0, it says do nothing to the target. Output will be 0, 0 again. Right? On the second one of this, the control bit is 1. Now you do a NOT operation of the target. So this will be translated into 1, 1. And the third line would happen, again, control bit is in 0, do nothing. So you get 1, 0. And finally, in this bit, the control is 1, so you have to do a NOT operation again on the target. So this will become 0, 1. Okay? So that is the gate. That is what the operation of this gate is. And now if I give you any 2-qubit gate, which is a state which is linear combination of this, you just create a linear combination of the same linear combination goes out. Yes, question.
Talking about universal computation, is it that, like you said, that single qubit rotation plus C0 is a combination? So any operator can be written as a linear combination of these or just a multiplication?
So it's a sequence of this. There will be some sequence in which you will apply these gates. Yeah.
It can't be a linear combination.
Yeah. So it's essentially your input state comes in. You apply some sequence of rotation with some sequence of control NOT on some complicated. You can always break any computation down into that.
You can't duplicate a quantum state, right?
Yeah.
So adding is not possible.
Right. So yes. So in this case, you keep on applying them in a sequence. You break them down in this sequence, and then that produces a generic state. Okay. Good. Yes.
Yeah, so since each state is being represented on that block sphere, each bit, so if I just have rotation, why isn't it possible to generate everything just by using these
Right. So this idea of entanglement, which is very key to all of this. So the basic idea is these n qubit state that we represent, this 2 power n advantage, that will only happen if you have entangled. You cannot break that state down into product states of individual qubits, because if you were able to break them down into product states, each can be just specified by 2 numbers. Okay? So if the fact that this is the entanglement, that you cannot break them down into products, so that's why you need something to generate that. Depending on state of 1 qubit, something needs to be done on the other. And that's why you need at least one entangling gate. Yeah. All right, any other questions? Okay, so very similarly, then the summary of all this is, well, I still need to tell you one more principle. So that's about manipulations and storing information. Okay. Now in the classical system, we saw once we have manipulated the information, reading out is just trivial. Okay, we read whatever state there is. But reading out in the quantum mechanical world, as you have already learned in the fundamental measurement postulate, is the fact that although you can work in this very large dimensional space, you can create whatever state in this 2 power n dimensional vectors. Once you start to read this, you cannot read out each component of these vectors. Right? You cannot get the information of alpha 0, alpha 1, alpha 2, and one measurement. You cannot just read out this whole quantity. What quantum mechanics tells me is the state will just collapse depending on the measurement that you're trying to perform. Okay? So for example, in this bits, the type of measurement we do is we try to do a measurement in some basis state, so which is either the so-called computational basis state. We try to perform the measurement and see whether the state which I read of this single qubit is 0 or 1. It will either fall onto 0 or fall onto state 1. Okay? Any generic arbit superposition of the 0 and 1 will just fall onto one of them. Okay? That's because of the famous measurement postulate of the quantum mechanics. And as a result, once I read this state, which can take any value on this sphere, right? If I give you any particular arrow, it will always be either 0 or 1 when I do the perform the measurement of this particular state. Okay? So in the end, I only extract one bit of information, although there is this whole possibility of this thing to be on the whole sphere. Quantum mechanics does not allow me to read, to sort of in one shot read all this information. I can only get bits generated again, which is very similar to the classical computer. Right? A particular bit can only spit out one bit of information in the end. Here also, although the state can be encoded in this very large space, reading kills this advantage in some sense. Okay? So that's why just making a quantum computer itself is not the only important thing. You have to create an algorithm, a software algorithm, such that the answers that you want to read out are spit out by this machine. Okay? And that process of building this algorithm is not a trivial task at all. There are only very few algorithms that are known where this machine will outperform classical counterparts. Shor's algorithm is a famous example of that particular algorithm. Okay? And we'll talk about some aspects of these things. Okay? But this is maybe another good point for me to just pause and see if there are any questions. The main differences between the two machines, quantum and the classical rules, I hope that is clear to you. And so why this will give us some advantage is what I want to move towards as the next step. Okay, good. Right. Okay, so combining all these ideas together, then we can think of what a universal gate-based quantum computer may look like. All you have to do is just keep crossing out classical parts from this and convert them into quantum. So rather than using bits, those things will be using these qubits, which are on spheres. So you have n qubits, and then they will be manipulated by gates, which will now can take any unitary values rather than being just 0 changing to 0, 1 changing to 1, or 0 changing 1, 1 changing to 0. Now you can do rotations, unitary rotations. So those type of gates you can apply, or entanglement type of operations, which are now allowed in this quantum mechanical world. So this will become unitary evolutions. Okay, and this you keep on applying to generate. The basic task will be to take some initial state of n qubits into any arbitrary state of these final n qubits. And if you can do this with some basic gate sets like C0 plus combined with some single qubit rotations, then you have a machine that is, you break down any function into just these combinations of C0 and single qubit rotations. Then the machine that results is what is represented here, is what we are calling a universal gate-based quantum computer. Okay, so that's the basic definition in some sense of this machine. Okay. And what its purpose is, what it is doing in the end is something like this, right? So you initialize this n qubit some initial state, and at each point you apply some unitary rotation to that n particular state, and finally you read out this particular state. It just spits out an n-bit number. Okay? So it does not give a 2 power n number. It gives an n-bit number. Even that n-bit number comes with certain probability. Each number comes with certain probability. What is the probability of a particular number? So this it can spit out possible 2 power n answers. Each comes with certain probability. Okay, so that is what a quantum computer is. And what is this pattern? That pattern is governed by what gates you put in between. Okay? If you change this pattern of these gates, you can change this pattern to something else. Okay? So in that sense, it's kind of like a sort of an interference experiment. It's generating some pattern of numbers, and that pattern can be orchestrated by orchestrating some gates. Now, if you can use this to generate a particular pattern of interest for certain particular application, that is the main question, right? Can you use that for doing something better than a classical computer in generating this pattern? If you can show that, then this machine will become useful. All right? Okay, any questions on this? Because this is probably one of the main message of what a quantum computer is for us. Right? It's a probability number generator. And the pattern that it can generate depends on what gates you orchestrate in between. Yes?
So just to understand the purpose, so basically you're saying that like the quantum computer is like a device that given an initial state you want to synthesize some given set of states with certain probabilities. That is the idea?
Yeah, it just does that, right? So it spits out some 2 power n possible answers with certain pattern. Okay.
And so to check whether we are really generating those states, that fidelity for it.
Yeah.
So then that will require a lot of measurements to know whether you are really.
Correct. That's right. Yeah, that itself is a complex task, right? And there's a whole field of tomography and things like that people try to do that. Now, where it will be useful is if this pattern is something like, let's say I want to generate one of the answers every single time. I can design some gates and it spits out that particular answer with almost close to 100% probability. Then I'm getting that answer in a classical way would be very, very challenging. But here it will give that very fast answer. Just to jump a little bit, and I'll talk about this a little bit, but Shor's algorithm is trying to do something like that. It is generating a pattern which is separated by the period of some function. You want to find a period of some n-bit function. If you can find that period, you can factorize things. Yeah, but finding that period is very, very challenging for a classical machine. Here you can exploit this interference phenomena to generate a pattern which will spit out that number very quickly. Okay? That's the fact that Shor exploited in his algorithm. Yeah. All right. Any other questions on this? Yeah.
It's like, how do you ensure like every time you're getting the same answers?
Oh, right.
Yeah, because like the bits are changing constantly.
Sorry, gates are changing constantly?
The qubits are changing, right? The probability is changing also.
Right, so the gates you kind of fix. You fix the particular gate. You don't change those gates. And of course, I'm forgetting about there are any environment interaction and there's some errors. Errors is the main killer of this, right? So let's say if there are no errors and I can make this unitary rotations, the state that will generate will always be the same exactly at that final state. But which place it will fall into, that is arbitrary, right? So for example, the final state lives in this Hilbert space spanned by these 2 power n numbers, 2 power n complex numbers that I was talking to you about. And the information whether it falls into one of these states is given by that complex number squared. Root square, right? So there's some probability it will fall here or fall there or fall there. That is what this generates this particular pattern.
So each qubit will have its own probability curve, right? I mean, and then how are we really adding that with gate?
Okay, so maybe what I mean by that is at each point you can write down the state. Okay? So this is some initial state that I initialize, let's say, some state psi, which is again broken down into I can write them into linear superposition of all possible bit strings of this 2 power n, right, with some coefficient alpha 0, alpha 1 and all that. So that's the state here, which I initialize. Then I apply a unitary gate to this. So this will be changed. What will be changed is these coefficients will change. Okay? It will change to some other coefficient. So they will become, let's say, prime. 1 prime after the first operation, right? And after second operation, they'll become some 2 prime and 3 prime. And the final state, it will be alpha 0 n prime, let's say, right? So these some new complex number. So taking these complex number into this complex number was the action of my quantum computer. Okay, this will remain fixed at every time, right? Unless again there's errors or things like that. If I forget about that, this is always same. Now finally I'll read this state by measurement. So these numbers will tell me what is the probability I'll fall here. Okay, so that will generate this pattern. If I change the sequence of gates inside, these numbers will change, and that will change the pattern. All right, any question? Yeah, go ahead.
Kind of a silly question again, but so initially we started out by saying we want some this universal gate computer is something that can generate any state in that span of 2 to the power states, right? But it seems to me now that we have fixed a certain sequence of gates, and so basically this is tailor-made to produce one particular state starting from a given initial. Right.
Yeah. So this is Sorry, go ahead. Yeah.
Right. So basically my question was, so if I really want to explore, get to any of the states in that 2 to the power n space, then I would have to make 2 to the power n devices.
Right. So what is meant by you will have to change the sequence of gates then, but you have to tell me a function that you want to realize by that machine. Similarly to classical machine, if I want to have an adder or something, right? Then there is a fixed sequence of gates that I need to specify, and this function circuit will behave like adder every single time. But if I want to do, let's say, a multiplier, I will become a new different circuit. But the basic constituents or building blocks of each of them is same. It's like AND gate. I can combine all of them together to realize all these functions together to build a particular machine. It will be very similar to this one. The whole thing is that can you realize arbitrary unitary transformation based on some basic gate set, universal gate set, then you're done. Okay? So that's the whole point. Yeah. Okay. Any other questions? All right, great. All right, so that's essentially what is a universal gate-based quantum computer. It's a probability pattern generator depending on what unitary gates I'm applying. Okay, and if I can generate arbitrary patterns, then that's a universal quantum computer. Okay. All right. So then the next question that we come to is essentially why do we want to build this machine? Why would it be powerful? Because in the end, if you compare it, right, it is generating n bits number, and that too probabilistically. Okay. I can use a digital computer to do n bits number, and I can generate a particular digital number with 100% probability in that. Okay, so why do I want to build a quantum computer then? Okay. And one answer perhaps could be to exploit this large 2 power n dimensional space. Okay. I give you n bits, n qubits, I have this 2 power n dimensional, some dynamics happening in this very large space. So can we exploit that, which is usually called quantum parallelism in the literature. Okay, and the answer whether just this quantum parallelism is enough by itself, the answer is no. Okay, no, just by itself it's not. Just by itself, which we have kind of alluded to already, right? Because although you work in this, the answer is also already just an n bit number in the end. Okay, so by itself this is not very, very useful. And just to sort of highlight this further, let me take some simple examples here. Okay, so for example, if I give you some Boolean function, okay, by Boolean function I mean the input can take 2 values, 0 or 1. Okay, and the output also lies in 0 or 1. Okay, so let's take a very, very simple example like this, and I ask you to evaluate f of 0 and f of 1. Okay, those are the 2 possibilities that this function can take, and I want to know those answers. Okay. Classically, how would I do it? I will have again a classical circuit which will implement this function, and I'll give 0 as input, see what the output is. I'll give 1 as input, see what the output is. So in 2 steps, I will be able to tell what the answers are for these 2 things. Okay. Now, let's say if the same circuit is implemented on a quantum computer, and this black box is supposed to represent that. Okay, so this is some unitary operator that corresponds to that particular function. Okay, so I can implement that. I don't worry about how I am implementing it, but let's say this is the function that's available, and it takes an input. That's the input line, and it writes the output in this qubit. Okay, so it takes 2 lines, and one line you give the inputs, and in this line you write the output for that particular state. Okay, and that's written in this particular notation over here, where the input line just goes through, and the output line is given by. So depending on what the value of this qubit is, of this particular qubit is, you get an answer here, which is given by this number. It may not be visible, so let me write it here. it's written as so that's the fashion in which this circuit is implemented. Again, not very critical for us. The main thing that's critical for it outputs f of x state. Okay? Depending on what the state of y is, if it is 0, this particular operation is the usual C naught operation that we have talked about. Okay? So this means that if it's 0, it gives fx. If it's 1, give the bar of that. Okay? So not of the fx value it can take. Okay? So in that fashion, we are implementing this particular circuit. Again, the main thing is that it can give rise to values of f of x. If I hold this line to line 0, it just gives the value f of x at the output. Okay? So that's the circuit. By you give 0, you get f of 0. You get 1 over here, you get f of 1 over at this point. Okay? So that's the two different circuits. Again, I will give an input, 2 different inputs. Once I'll give 0 and once I give 1, and this quantum circuit is evaluating that. I'll read this particular line. I'll get the answer f of 0 or 1, f of 1. Okay? Here also it takes me two steps in order to do this. If I query my circuit in this particular fashion. Okay? But now let's try to come back to this point of parallelism, quantum parallelism. You may think a better option would be to do something like this. Okay. This is a single qubit rotation gate which will take your state 0 and convert it into a superposition state of 0 and 1. Right? So remember, all manipulations are allowed which can do rotations on the Bloch sphere. So I can start from 0 and bring it to the equator, which is 0, a linear combination of 0 and 1. Okay? The gate that does this is given a special name. It's called Hadamard gate. So that H stands for that Hadamard gate. Okay? So if you give this initial state, I do perform a rotation. I can create a state at this particular stage, which lies at the equator, which is actually a linear combination. It is a superposition. It's neither 0 nor 1. It's a superposition of both 0 and 1. So then I may think that at the input, I can query this quantum computer by giving 0 and 1 both at the same time. And at the output over here, the state would be f of 0 plus f of 1. There will be some linear combination of that particular state that will be generated. So in one go, it may look like I have both f of 0 and f of 1 evaluated by my machine. Right? So that is the meaning of quantum parallelism, that I can use this superposition, which is not allowed in my classical world right now, to evaluate, at least evaluate by my machine, these numbers in one go. Okay? But again, here's the where main measurement postulate comes. I cannot read those two states simultaneously, but if I do a measurement, it will either fall into this one or it will fall into this one. In this particular case, it will, with a equal probability, it will give me this with 50% probability. I'll give that and give this. So in one measurement, one go, I will not be able to retrieve the information, although my machine has calculated it. Okay? And that's the main thing that I want to highlight, is parallelism by itself is not very useful. Okay? But let's say if you want to do something different. Okay? Also, one more point I should highlight to make connections with the probabilistic computing that you'll hear in a bit is this fact that I've been stressing, that this large 2 power n space that's there in the quantum world, actually that feature can be built in the classical machine also. Okay. Because I was just focusing on deterministic machines, one can also think of storing information not in a bit which is up or down, but let's say, what is a 2-level system in classical world? Well, there are some 2 states which are favored. So this could be a magnet which can point up, which have lower energy, and then there's another state which has a lower energy, which is pointing down, right? Those are my 2 bits of information I can code. And most of the time I'll see this bit being here and this bit being here. Okay? But I can think of lowering the barrier between those 2 and turning on some temperature, let's say. Then what I'll generate is a fluctuating bit. Okay? This bit will keep on jumping between 0 and 1. Okay? And there'll be some probability to be in state 0 and some probability to be in state 1. I can encode information in this probability, which is like an analog number. All right? I can, if, for example, this bit also allows me to vary the barrier like this, I can force it to be in this state more often. So I can change this probability of observing this bit either in state 0 or in state 1 and encode the information in probabilities of this bit being. Then the state of this system is also given by a vector with just 2 probability numbers, 2 numbers that will specify me what is the probability to find here and what is the probability to find there. Okay? So then I can convert this bit, rather than being digital, I can convert this also into an analog bit, right, which can take continuously. In single bit, I can store very large bit of information, right, because now it's in these probability numbers which can take continuous values from 0 to 1. Okay? And then if I combine sort of n of these numbers, Then to specify a particular state, I need to tell probabilities for each one of them. What is the probability of each one of them? And it can take, one of them could be here. When one bit is here, the other bit can be in any of the two of these cases. So I will again get this 2 power n number of pieces of information to specify the state of this. So the fact that this is unique to quantum is not really true, right? Even in classical machines, I can build this if we focus on so-called analog computing rather than digital computing, right? And this probabilistic computing is one example of this thing, right? So then this large space dynamics I can also have in the classical machine, right? Then really what is the advantage of this quantum computer? And really the advantage is combining these large 2 power n space dynamics with the fact that you can have interferences, coherent evolution in this large 2 power n space. The fact that and to highlight that, let me try to focus on this probabilistic machine, for instance, for example. So let's say if I have this n bit input. Yeah, sorry, you have a question? Yeah, okay. So the state could be again this 2 power n vector. Right, if I have n probabilistic bit, I also need to give you 2 power n numbers, right? And these are, each of these coefficients are probabilities now, p1, p2, what is the probability of particular configuration, right? Then you can do manipulations on this thing. So the manipulations are also given by some matrices. Will transform one probabilities into another probabilities and another probabilities, and that's how you'll, at the very end, you'll generate a probability of numbers at the very end. But there's a very fundamental difference in which this final probability is generated in this machine versus the way probability is generated in the quantum computer that we just talked about. And the key word that differentiates between these two is the fact of interference. Okay? And let me try to highlight that particular point. The way you should think about this is, each of these, since these are probabilities, this can only take values from 0 to 1. A number, continuous number from 0 to 1. But in a quantum computer, these are amplitudes. These are states which have vectors, complex numbers. It can be negative, it can be complex, it can have any phase factor associated with them. Okay? And then, but amplitude is not what we read. The way we generate the final probability is we transform all amplitudes with each other, and final amplitude gets squared to get you the probability. Right? But during this evolution, I'm adding up amplitudes of these wave functions and then squaring to generate a probability. Do you recall any particular like a physics experiment that does this? Sorry? Double slit experiment, right? That's exactly what a double slit experiment is, if you recall, is you have 2 slits and you have some detector which detects some energy, let's say, deposited at that detector at the very end. But if there are the objects that are impinged on the slits are waves, right? The final energy that's deposited, the way it's generated is you add the amplitudes first of these two waves and then square it to get the energy of that particular deposition, right? And during this adding amplitudes, you are allowed to make one of these amplitudes positive, another amplitude negative, and you can cancel the 2 out, right? And you can, that's why the pattern that you generate here is very distinct if this is waves, if the basic objects you're working with are waves as opposed to particles, right? In that sense, this probabilistic machine, although I can work in this 2 power n dimension, I'm restricted in terms of the interferences that in fact, I'm not allowed to do interference in this machine. Yeah, I cannot have negative probabilities. Okay? In some sense, I'm allowed a negative probability here to add these negative positive numbers, in fact, phases, and generate a particular pattern in a very efficient manner. The same pattern, if I want to generate in classical computer, I will have to do something very different. Okay? And then the question is, this interesting pattern that you generate, can that be useful? All right? But that's the main difference between the two. And I think in words of Feynman, he pointed out that it's really these negative probabilities that are that you can generate in this quantum computer is very different from the classical ones. Yes, question.
So regarding the quantum parallelism, like in classical computer, there's a problem called data racing. It's like
I see.
When traditionally we started from single core, now we have like multiple cores, right?
Mm-hmm.
So when we get data into like the CPU cores and all of that, we need to manipulate the state of memory.
Mm-hmm.
So what the problem arises is that when we get the data in one core, it really manipulates the data in memory. So that the second core has no idea what's going on.
Mm-hmm.
And that needs to be like synchronized or communicated properly.
I see.
So how do you really solve that kind of data racing problem in like quantum computer?
Right. So I might not have understood the question very well, like how that translates into a quantum machine. the way parallelism happens is sort of naturally in this machine, right? So each qubit can take any of these values 0 and 1. It's really you who are deciding the gates. Once you decide that gate, the state will evolve again, barring any errors that are occurring in the environment.
So we can talk about later. But
Sure.
basically, what is the memory access pattern in quantum computer?
Memory access pattern. Again, here I don't really have, memory will only come if I want to store this information somewhere. Right now, again, once gates and qubits are given, it will keep on generating always those numbers. It will keep on splitting those numbers with those probabilities. So I can always, whenever I read, I'll generate some n-bit probability numbers. I don't have to worry about the memory yet. But if you want to store that somewhere, then where the memory would come into play.
So do we normally just like when we want to calculate something, we just send the data, then we get it out of it?
Right. So you would usually what you will do is you would initialize it in a particular fashion, right? Or every single time you'll try to initialize in the same state, and to generate this whole probability curve, you'll keep on reading the final answers, and that will fall into this probabilistic pattern. Right. Yeah. At the architecture level, you may be right that eventually, if you want to do something with these probabilistic numbers, you have to store them somewhere, and then how do you build sort of a memory to keep those numbers? Perhaps those type of questions are. I don't think. Well, people are thinking about what architectures, given these new rules, are there. Okay. Yeah. So we can maybe talk a little bit about it. Yeah. All right. Right. But the main difference between these classical and quantum machines is the fact that now I'm allowed to do interference in this large 2-power n-dimensional space. This is a unique feature which is not available to me yet in the classical computer, and can we exploit that to do something useful? Okay. All right. So any questions on this part? I hope the main difference is clear between the two things, right? Let's see how I'm doing on time. Okay, I have just a couple of minutes, so maybe I'll finish off this particular piece. Give this main information that why do we want to build and how do we build. We can take a break and talk about the how part in the next thing. Okay. All right. So that's exactly what I'm talking about, that it gives combination of parallelism and interference, which is also usually called quantum coherence sometimes, which I can exploit in these machines to generate a particular pattern, which if I want to just generate this classically, it will take me much more resources. Okay? Yeah. So that's essentially to this interference thing. And just final point to highlight, this fact was first highlighted by I think, to the best of my knowledge, was first highlighted by Deutsch in his famous Deutsch algorithm. Okay, and we'll take a look at this very simple algorithm as an example of when you can use this interference to solve something faster than the corresponding classical machine. Okay. So here's the problem statement that it's kind of like a challenge problem. It does not have a utility in a sense, in the sense that you cannot use it to perhaps generate taxes or tax it. But the main thing that it does the main message it gave to the community was that there is something unique in these quantum machines. Okay? Right, so the problem was the following. So it's again the same 2-bit example. That is, let's say if I give you an unknown function, okay? And this functions, it's a single bit function. That is, it will take input either 0, 1 and generate outputs either 0, 1. So I can write 4 possibilities of these things, right? So I can take 0, 1 that can be mapped onto 0, 0. 0, 1 can be mapped onto 0, 1, or I can map 0, 1 onto 1, 0, or I can map 0, 1 onto 1, 1. Okay? Those are all 4 possibilities of these functions. Okay? These functions comes in 2 categories, which are labeled by 2 different colors here. In one case, this function is called balanced. The reason it's called balanced is because both the outputs are produced in an equal fashion by this function. On the other hand, here, this is called a constant function. That is, both the inputs are taken to just one output. Okay, so that's a distinction feature of this function, right? So it can be either balanced or constant. And the challenge problem that Deutsch proposed was, let's say if I give you a machine where this function is given to you, it's an unknown function is given to you, and your job is to find out whether it's balanced or constant. How many queries or how many steps it will take for you to figure this out. Yeah. Classically, one way to do this is you just give both inputs and check what the output is. If they go into the same output, then it is a constant machine. It's a constant function. If it goes to different outputs, then it's a balanced function. Okay? So those 2 steps will be taken by you. Okay? But now what Deutsch said is, if I give you a quantum machine, then you can do this in just 1 step. You can distinguish between whether the function is constant or balanced in just 1 query. And there we'll exploit this fact that you can build things in quantum, you can give both superposition as an input to this machine, and you orchestrate the query or gates in such a fashion such that only if the function was balanced, one of the output line lights up. The pattern is that you get output 1 every single time, and if it is the other one, you get output 0 every single time. Okay? And just by one query, you'll be able to tell. Okay? So the fact that you can do interference and generate a particular pattern, you can exploit that to solve this particular problem in a much faster way than the classical machine. Okay? And this is the circuit that was proposed by Deutsch, where this is the same box that we have already discussed. If I give you a function, you can implement a unitary function like this, for instance, and then the way you query it, now you are querying it in a quantum machine in this following fashion and reading out in this particular fashion, where each of these H are Hadamard gates that we talked about, which does this rotation on the Bloch sphere. Okay? And the inputs that are given to this are 0 and 1 at this particular stage. So what happens is, what Hadamard gate does is 0 it brings to the equator with the 0 plus 1 superposition, 1 it brings to the superposition of 0 minus 1. Okay? Again, it's not a trivial task to come up with these gates, because that's the whole heart of the algorithm. That's what Deutsch did, right? How do you orchestrate these gates to get the probability pattern you want at the output is what is an algorithm in itself. You have to design. This is what he designed. Okay, so what happens in this particular case is, so once this particular input is given to this function, we can evaluate actually what will happen at the output stage over here. So that's the state, that's the combined state at the input of the circuit. And then what you can do is you can walk through what is the output state that you'll generate at by this unitary gate. The simple way to do this is, when the x is 0, you'll get f of 0 at the output at here. But for that, y should also be 0. Okay? So when the input is 0, 0, that's the state. So if I write the state at this stage, it's a product of these two things combined together. The input state is 0, 0, 0, 1, 1, 0, and 1, 1. So those are 4 states I need to operate on, with the following rule, where whenever y is 0, spit out f of whatever the x line is, but whenever y is 1, spit out the bar of f of x, f of thing. And that's what this C0 operation tells you. That's how the circuit is. If you walk through this particular exercise, you'll see the final output can be written down as this. Okay, so there are 4 states that are generated at the output. With 0 comes with f of 0, and then 1 comes with f of 1, then 0 comes with bar of f of 0, and 1 comes with bar of f of 1. Okay, those are 4 possible with particular signs coming from these signs over here. It's this fact that you can design signs and things like this is not possible in the classical computer. Okay? So that's the final state that will come out of here. Okay, so now what will happen if the function was constant? Okay, that is, both of f of 0s and f of 1 gave you the same bit. Okay, and let's say that bit is going to 0. Okay, so let's say f of 0 gave me 0, f of 1 also gave me 0. Here f of 0 bar will be the opposite of what f of 0 gave me. Okay. So in the sense, if the function was constant, doesn't care if the input is 0 or the input is 1, these two brackets are same. Okay, that's the basic idea. If the function is constant, and I can take this bracket out, I can factorize this into 0 plus 1. Okay, so what that stays means that this bit over here will be in the superposition 0 plus 1. I can factor this out if the function was constant. Right? And if you take that 0 plus 1, it turns out Hadamard gate is inverse of itself. Okay, so you can write the matrix down, it's inverse of itself. So if it takes to superposition, it gives you back to the state 0. Because the final answer will be 0, and the line 0 will lit up if this function is constant. Okay. On the other hand, if this function was balanced, what will happen is, let's say f of 0 was giving me 0, was going to 0, then f of 0 bar will be 1 over here. And since f of 0 was going to 0, if the function is balanced, f of 1 has to go to 1. Okay. And then this will be reversed. So this was 0 minus 1, this will give me 1 minus 0. Okay. So that there's a negative sign that comes in here. Then I can take this thing out. So the state will go to 0 minus 1 for this particular line, rather than 0 plus 1. And that taken to Hadamard will go to other state, 1. Okay. So in a single shot, if I read this, if the function was balanced, I'll see output as, in this case, the output would be 1, 0. And if the function was constant, if the function is constant, the output is 0. If the function is balanced, the output will be 1. Okay? So in a single go, I'll be able to distinguish between these two states. The fact that I can bring them in superposition and do these interferences to generate the pattern that I wanted allowed me to do this. Okay? And that's what Deutsch conveyed to the community. After this, there was a whole flurry of activities which tried to exploit this superposition and things like this to generate desired patterns to solve challenge problems. And various sort of algorithms were discovered after that. For example, Deutsch and Joshua actually generalized there from the single bit to n-bit implementation. Then Bernstein-Vazirani gave a way to encode secret keys inside functions. And those secret keys can be spit out in this n-bit answer. That answer that you want, by designing gates, you can at 100% time give that secret key as an answer in single shot, as compared to things like where you will need, in classical machines would take exponentially large number of trials to figure that secret key out. And similarly, Simon also had a secret key information. Then came the famous Shor's algorithm, which as I mentioned, the pattern that it wants to generate outputs a period of a particular function. Okay. So in general, if you think about it, the basic idea is if you want to calculate some global property of a function, okay, so not want to get each value of the output of the input bit f0, f1, no, but if you want to get some global property, let's say period of a function or some sum of all the input of the inputs. If the answer comes in this particular fashion, where the answer is just one or few unique answers, then you can use this interference and the readout, design gate such that the readout, which will only give some n-bit answer, will just give that particular answer. Okay. Then you can take advantage of this quantum computer over the classical. So it's not a machine which will replace all our digital computers, right? It is something which will have special purpose, and you have to come up with good algorithms. Just if not more complicated, it's actually equally important to come up with algorithms that can solve where these machines can be used for. Okay? And some famous examples more recently are solving quantum mechanics itself, using to find properties of these quantum materials. You can use these machines for doing that. And potentially, it's a probabilistic machine which is generating patterns not possible in the classical machine. So hopefully, that can be used for machine learning applications. Again, the answer is not clear. It's still in the research domain, things that people are looking at. So those are some of the examples why we would want to build this machine. Okay? And this is probably a good stopping point with this last figure that I want to highlight here is kind of there are all the classes of computation problems. You can break them down into things which can be solved in polynomial resources. Those are called P problems. Then something which cannot be solved in polynomial resources are the non-polynomial types. Okay? And it is widely believed when people came up with this factoring problem, when Shor came up with this factoring problem, it is something which, at least till date, there's no classical algorithm that can solve it as efficiently with polynomial resources as can be done with the quantum computer. And that is kind of believed as a fundamental law of quantum mechanics, where of computer science, where people believe that since this belongs to this problem which cannot be solved by many smart people till date, that means it perhaps does not belong to this P class. And as a result of that, if quantum computer can solve that, then we have a machine which can solve some bigger set of problems than this problem. And that's why people are investing so much effort into trying to build this. But what exact problems, that itself is an open question at the moment. Okay? So this is where I'll stop, and in the next part, I'll focus on how we'll build this machine superconductors. Okay, thank you. Take any questions.